x cubed plus 3x tells e raised to the power negative 3x, hey, you're looking good, very sexy today. E raised to the power negative 3x says, well, thank you, you're looking good yourself. In today's video, we're talking about complementary functions and particular integrals when solving differential equations. Complementary functions. As you know, it is quite common for the coefficients of y and its derivatives to be constants in differential equations. In other words, when you have a differential equation, the coefficients of the term in y and dy dx, d squared y on dx squared will be constants. The general form for this kind of differential equation is, for first order differential equations, it will be dy dx plus by equals some function of x. A and b are constants. So we have already seen how to solve these kind of differential equations by using an integrating factor. However, we are going to look at a second method of solving these kinds of differential equations. The general alternative method for solving these equations is useful for when you will be solving many higher order differential equations, let's say second order differential equations or third order differential equations. First, you find the complementary function. In other words, we call it just the CF. It is the general solution to the homogeneous case of the differential equation. This means you simply take the side that has the y's and you equate it to 0. You keep away the f of x, the function of x, for now. And then you solve it to get the complementary function. Then you find a particular integral. That particular integral is any function that will satisfy this equation. We will see about different ways to find particular integrals depending on how f of x looks like. And then the general solution will be the sum of the complementary function and the particular integral. Let's look at different ways of finding complementary functions. If we want to find the complementary function, we need to learn the general solution to the following differential equation. So, for instance, if we have a dy dx plus by equals 0, then we can rearrange it to have something like this. That will give us, if we solve that, we get y equal a e raised to the power negative b over ax. We already know how to solve that for first order differential equations. And so we can use this to solve the homogeneous equation. Let's take an example. We have the differential equation dy dx plus 3y equal e raised to the power x. Let's write the homogeneous equation down. Dy dx plus 3y equals 0. And then we can rearrange it to solve for y. And so we get the complementary function y equal a e raised to the power negative 3x, where a is an arbitrary constant. Now, how can we find a particular integral? So for finding the complementary function, it's not a problem so far. But the particular integral, we have to follow some some stated rules to find the particular integral. If we have this differential equation, which we saw before, if we want to look for any function that satisfies this equation, this function on the right, f of x, will give us a clue of what that function could look like. As you can see, you have a function you multiply it by some constant, and then you differentiate the function and add them together, and then you get e raised to the power x. So what does that tell us? It tells us that the function y must be some exponential function. It must be some exponential function, and so it should be a e raised to the power x, something like that. If we substitute this into the equation, we get a e raised to the power x plus that, and then we get a equal 1 over 4. So it means that our particular integral is 1 over 4 e raised to the power x. And so the general solution of our differential equation will become the complementary function plus the particular integral. We can verify this. We can substitute this into this differential equation and see that it satisfies the differential equation. Okay. There may be different cases for f of x, like you have a dy dx plus by equal f of x. Different functions f of x, we will have different ways to find the particular integrals. If f of x is a constant term, then the particular integral should be some constant. If it is a linear function, let's say f of x is some function of say px plus q, then our particular integral will be ax plus b. Then we look for what is a and b. If it's a quadratic function, then our particular integral will also be quadratic. If it's an exponential function, then our particular integral will also be exponential, as we have seen already. And if it is any trigonometric function, then our particular integral will also be trigonometric. So if it is sine px or cos px, then we will have a cos px plus b sine px for our particular integral. Okay, so let's review the steps before we move on. So first, you find the reduced or the homogeneous equation and hence the complementary function. Choose a trial function and find the particular integral. Find the general solution by adding the complementary function and the particular integral. Again, here is the rule for finding particular integrals. Okay. Example. Let's solve this differential equation 2 dy dx minus y equal 2 cos x. For our complementary function, we write down the homogeneous equation, and then we solve the homogeneous equation to get y equal a e raised to the power half x. And then we find the particular integral depending on the right hand side of that equation. It is trigonometric. It is 2 cos x. So our particular integral should be a cos px plus b sine px. Remember that the value of p should also depend on the value that is before x here. So since we have cos x only, so it should be a cos x plus b sine x. And so now we will differentiate that and substitute in this equation to look for p, a and b. Substitute, rearrange, form two equations with two unknowns. At this point, what we have done is we equate the coefficients of each of the terms. So the coefficient of sine x should be 0 because there is no sine x on the right hand side, and the coefficient of cos x should be 2. Since the coefficient of cos x on the right hand side is 2, So from there we can get a and b, and therefore we can get our complementary particular integral. Then now our general solution should be the sum of the complementary function and the particular integral. Thank you.